Okay, let's start next category of security, yeah, cyber security. So the next one we said we will look authentication based defenses, yeah. As the name says, you need to do some authentication, yeah, to basically log in into some system. So let's look first this. So typically what we do is something like static authentication, yeah. So static means like it's done just only one time, yeah, at the very beginning. Once you log in into the system, then there is no authentication, okay. So in a typical scenario, a user sends a request and then there is some server where the authentication takes place, and if your credentials are fine, it will kind of return a green response, you will be able to successfully log in. If not, there will be like bad response, yeah. And these authentications use this kind of protocols, yeah, okay. So I have put a question. So what do you think about this kind of static authentication? Is this enough to secure a system or not? If not, then why do you think it's not? Okay, let's go that slide. Okay, if you open the same web page, the question will change, yeah. Let me see for me. Yeah. So this is typical way we log in into any system, right? Know that authentication token can be used by hackers also to gain access to user profile. Yes, it can be. So basically you may say login credentials can be used by someone else, right?
It's more like cookies.
Yeah, and we need to verify the sender. That's important one. We need to typically verify the sender, yeah. Even if some authentication has happened, there could be some extra mechanisms to verify, yeah. Once the passwords are leaked, then anonymous person can access the profile. Correct? Yeah. Okay, so let's look like I have my own logic, yeah. For me, there are lots of situations this kind of static authentication is not enough, yeah, and we will see like why it is not enough, and then we will see what can be done to fix that, okay. So we go here. I think it takes some time to load. So there are some issues with this kind of authentication, yeah. So I would say in summary, these are inefficient in dynamic and high risk environments. Okay, let's look what can be the potential issues in this dynamic and high risk environment. So one of the issues can be spoofing, yeah. So spoofing is like someone is trying to mimic your behavior, okay. So what attackers can do, they exploit vulnerabilities by mimicking the hardware and software configurations of legitimate device to gain unauthorized access. So even though you have authenticated, yeah, there could be another attacker, he's trying to use the same configuration. He doesn't need to do authentication. He's trying to mimic the same behavior of the device and then trying to gain access in the network, yeah. Some example could be the IP address, yeah. Just like each device has an IP address, right, when it's connected, but someone else can assign some IP address to his own device, the same one, and then he can try to come in the network. Yeah. Similarly, it can be done with the MAC address. Okay. So in this kind of scenarios, you can see like even though one-time authentication is done, but then with the system behavior with that authentication can be copied or spoofed, and then someone else can log in the same network. Yeah, pretending like that is also a legit person. Okay. Another thing could be cloning. So it's like copying, yeah, and trying to clone to other device as well. So more or less like spoofing. Yeah. Okay. The third one can be spill. Yeah, as the name says, spill. Yeah, too many things. Yeah, throwing so many things. Yeah. So someone can create multiple fake identities in the network. Yeah. So for a real authentic device, someone can try maybe same IP for 10 device, and he can try to log into in the network. Yeah. So although you have done the static authentication, but someone may be able to come in the network. Okay. Someone can also do some physical tampering. Yeah. So they can remove and add something. For example, they can connect some jumper or something to connect with some external device. Okay. So I would say these are some of the problems with static authentication. Okay. So I have a question here. So like those spoofing, spilling, cloning, yeah, those things, how do you think that can be fixed? So in summary, how static authentication issues can be addressed? What do you think? We go to that slide. Yeah. So in essence, you have to stop this spoofing, right? You have to stop cloning. You have to stop spill. How that thing can be done? We need to verify the authenticity of each of the transactions. That's a good example. Yeah. So it's like whenever any user is trying to get access or to some network, you can try to authenticate for each transaction. Yeah. But then you may end up authenticating maybe too much. Yeah. Your user might be so irritated, right? And I think even if you use multi-factor authentication, this issue will still be there. Yeah. Because someone is just cloning the device after authentication has been done. There could be session tokens. Yeah, that's nice idea, but it's can be difficult to find out like how long you want the session, right? 10 minutes, 1 hour, something like that. So by using dynamic authentication or using multiple authentication layers for critical tasks like for transaction, I think you are getting closer. You need some kind of dynamic authentication. Yeah. So dynamic can also mean like continuous authentication. Yeah. But you cannot ask a user to keep entering the password all the time whenever he asks for something. Yeah. So there are some ways how we can do dynamic authentication. Okay. Let's look. Okay, so the fix to those things is continuous authentication, or you can say dynamic authentication. Yeah. So we recently have published a paper. It's called continuous device to device authentication, exploiting crystal oscillator impurities. Yeah. So in each processor there is a crystal oscillator, right? That's basically making the clock. There is some impurity into that. So we can use that feature to do continuous device to device authentication. Yeah, we will come to that how exactly this can be done. Okay. So this is the high level overview of the continuous device to device authentication framework. So it has basically two steps. Yeah, one is identity establishment. So it's like, let's say there is a network, a device wants to connect in the network. So first we need to find its identity, or you can say first we need to find its fingerprint by using some characteristics or features of the device. Yeah, like I said, crystal oscillator impurities, that's one of the features you can use. And after that is done, you can keep doing continuous authentication by storing the identity in the server. Yeah, so let's go a bit more details here. Yeah, so how you can do this identity establishment phase? So it's like each device is kind of, you have put login password. Yeah, after that you can extract some features of the device and you can do some feature processing and you can generate some fingerprint. So this will be like very unique to that device. Yeah, and it typically leverages natural hardware imperfections. Yeah, and one of them is crystal oscillator impurities. So how this is done, how we have done it, it's like for each device basically you kind of put a nope instructions, it's not doing anything, and then for crystal oscillator impurities you just capture CPU cycle count. Yeah, and then you store it for some time, then you reboot the device, and then you store it again, you reboot the device, you store it again for some time. Yeah, and then over all some executions you then come up with some fingerprint that will be very unique to that device. Okay. Now in continuous authentication phase, basically this continuously track the change in the device behavior. So like when over the time it's tracking the device behavior change, and it applies dynamic authentication policies. So basically it kind of decides some timeline when the device has to be authenticated with the fingerprint that is already generated. Yeah, it's like a static authentication is done. Yeah, after that you store the fingerprint. Yeah, and over some period, depending upon how critical the application is, we will come to that, this continuous authentication over the server can take place. Okay. So this, like I said, follows a bit of client server model. Yeah, each device is a client and where the fingerprint of the device is stored is a server. So like I said, fingerprint is stored at the server, a client device needs to be continuously authenticated, and the server end performs the authentication, which can be on the server or that can be on a deployed router as well. Yeah, let's say in a home there are a lot of devices, right? So all the fingerprint of each device can be stored on the router. So if someone else tries to basically clone your device or spoof your device identity, and if there is this kind of continuous authentication, you will know, like even though they know the login and password, but the feature will be different for their device. Yeah, like I said, each device has all different features. Okay. The reason is there is some imperfections when they are manufactured. So that imperfection can be used. This is fingerprint of this one, this is fingerprint of that one. Okay. Okay, so now I have a question. When do you think this continuous device to device authentication framework won't work? There could be some situations it's not going to work. Yeah, I would say we already have seen it. Yeah, so if someone gets your ID and password, yeah, and then basically then this is no point. Yeah, they can always log in. Okay, so that's one of the situations. So first you ensure ID and password, that should not go anywhere. This one is like if someone authenticated, someone tries to clone your device, same identity tries to create, then basically it can stop. But if your password is gone, everybody can do it. Yeah, okay, good. Let's see, it stops here. Okay, so like I said, there's something called like device authentication timeline. Yeah, so when do you decide how frequently you need to authenticate, or like how late you want to authenticate? So let's look the first one. So here you can say for one device, this blue line is something called like identity establishment. Yeah, it's like fingerprint generation and storing in the server. Yeah, and initially you do some kind of continuous authentication. Yeah, but if your device is low risk, yeah, you don't need to do authentication so frequently. You can do at kind of some higher interval, yeah, maybe every 10 minutes or something. But if the device is high risk, you always want to do at more frequent intervals. Yeah, and how this interval is determined, so we developed something called like device authentication score. So it's kind of says how authentic the device is, and based on that, how frequent or how less frequent the device needs to be authenticated. I think we are not going into the details of this formula, it's in the paper, I will point out. So it's like if device authentication is more than 80%, it is a lower security risk, which means you don't need to authenticate so frequently. Okay, so which means high or device authentication score indicates there is huge confidence, there is no problem. Yeah, so score is high. Similarly, if score decreases, it becomes medium security risk, and in this range we have classified that this is high security risk. And if your device authentication score is less than 50%, which means there is kind of no confidence whether it should be further authenticated or not, because you assume this is some attacker. Yeah, so in that case you can say unauthorized. Yeah, you can basically stop the access of that particular device. Yeah, for example here. Yeah, so that device can be eliminated from the network. Okay, so this is kind of continuous device authentication timeline. And these are the some evaluation results. So here the first column shows devices. So we have device 0 to device 10. So these, all of these are Raspberry Pi board, yeah, you might have used. And then the second column shows precision of change. So it's like the fingerprint is stored, yeah, and when it is monitored later on, how much is changed over the time. Yeah, so you can see like if the change is low, the device authentication score will be high, right, which means it doesn't need to be authenticated so frequently, so the risk will be low. Yeah, but if this change is a lot, that means it's varying too much from the fingerprint that is stored, right. So you can see the device authentication score is very low. In that case, you can assume like you don't need to give access to that device in the network. You can say unauthenticate. Yeah, okay. So kind of here you see we do not have lots of device, but recently the student is trying a lot of like 50 of the Raspberry Pis, and kind of so that this range can be a lot. Yeah, but we have seen like low and high score device as well. Yeah, so here you can see this precision changes has some values. Yeah, kind of 5.2, and then device authentication score is around 52. So if, according to the previous bracket criteria, it falls into high risk. Yeah, so it needs more frequent authentication. So it can also be over the time the same device can go into different categories. Yeah, maybe at the beginning it was 0.02, this precision change in the precision, but after some time it can become 3.08. So depending upon how much the feature of the device is deviating from the stored fingerprint, you can decide how frequent or how less frequent this continuous authentication has to be done. So, it is not always the same for one particular device, it keeps changing depending upon the precision of change. Okay? Any questions? No? So, for more details, you can look into this paper. I think this was recently presented. I think I already have told this is a work with one of the company who produces routers in the UK. So, they have like a huge network. So, it is British Telecom. So, they want this kind of techniques because in their router there could be lots of devices that are trying to access, but sometimes there could be attack. So, just to make sure in their customers router they are not unauthenticated, or not attackers accessing that. Yeah. Okay. I don't know when this is going to come into the product, but it can be at some point. Yeah. So, it is like in your home there is a router, there is lot of devices connected to the router, right. Then for each device at the beginning you do multiple restart, yeah, and in these restarts you collect a feature. In this one I said it was cycle count, yeah, and then over the 5 or 6 restarts you make a fingerprint, you store that in the router. So, if someone else tries to clone your device, their fingerprint will be different, and if it is deviating too much, you can kind of say, the router can alert you like there is unauthorized access or unauthorized addition of some device in the router. So, this way unauthorized access can be prevented. Okay, any questions on that? No? But you can see this is interesting, yeah. Attackers have lots of ways to clone your device, or you can say copy the features of the hardware and software and then mimicking like it is actual, yeah. It is kind of like social engineering, yeah. Someone tries to call you from maybe bank or something, so kind of, yeah, they try to clone not the person, rather the device. Okay. Yeah. So, the next one I want to cover is work by another PhD student, is video manipulation attack in IoT environments. So, as the name says, there is some video, yeah, it is playing, and there is some manipulation of that to do the attack. Okay. So, let us look for some motivation, yeah. So, if you look lots of IoT systems like flood monitoring, they rely on real time video feeds, yeah. So, there are a lot of countries, I think this figure is, I do not know, not from India. So, this student is from Nigeria, they have a lot of flood problems. So, there are a lot of cameras that are getting streams and sending to the server, yeah. So, like flood monitoring basically relies on videos, yeah, and these feeds are vulnerable to manipulation attacks. So, what does it mean? When the video is going from this point to the server, someone can do something in the middle or someone can do something at the storage point, and then it is actually not that video, rather some other video, yeah. And this can be done in these ways, yeah, like replay. Replay is something like you store another video in the device, but you replace it with the previous one, and it is just playing the same video again. Okay. Frame injection and hijacking, I think I will come to that in a bit, yeah, what exactly are those. So, one question here, where else video manipulation attacks may happen? So, we saw IoT environment, yeah, like the flood monitoring. Where else do you think this kind of video manipulation attacks can happen? Okay, let me see this one. Okay. Banks. Okay, I think I was thinking that example. Are you thinking to kind of rob the bank? I mean, you might have seen some movies, right? People just maybe these movies Doom or something, they were all like that, right? They go hack inside the physical premises, upload some video, it's not the current but the previous one, yeah? That is exactly replay attack, yeah? They play something else repeatedly and it's not the current but something else, yeah? So of course, if you want to rob the bank, you can do that, yeah? I think lots of movies, yeah, lots of movies that. Hotels, yeah, can be done. I think deepfakes is a nice example, yeah. So it's like very similar video, maybe the feed is for flood monitoring, but you may say like there's no flood, yeah. So it is kind of, it can cause some kind of disastrous situations, okay. Online streaming, of course, like always you can replace some kind of unwanted contents, yeah, with something that you want, okay. But I think best example is banks, yeah. You can go like feed something that it's like yesterday's and then in background people can loot it, yeah. Good. So now you know where else video manipulation attacks may happen. Okay, hopefully this will move slowly. Okay, so now we talked a little bit about replay. So now let's look at additional attacks and detection, yeah. So replay, like I said, you take some pre-recorded video and replace with the real-time feed, yeah, just to again some previous video. There could be frame injection attack, so it inserts altered frames periodically. So it's like that, like typically in camera there are like 15 or 20 frames coming, yeah. From time to time you replace with something else, yeah. So it might be there was a moment that there was critical information, but then you confuse the person who is really kind of monitoring the video, okay. Another one is the stream hijack. So it's like something is running, yeah, and after some point you take the control and you replace the content with something else, yeah, but then it's again whole new video or something like that, okay. So it's after certain point you replace it. But what are the challenges with these attacks? So basically these attacks modify video either in bulk or at fixed intervals. So you can see, yeah, in the replay it's like everything is replaced, right? In this one also everything is replaced at one point. Because of that, it's very often easy to detect it, yeah, because there's huge change. So anyone can monitor, yeah, any human can monitor, or maybe there is some kind of monitoring in the processor that can also detect it, okay. So these attacks are disruptive, yeah, but they can be detected easily, okay. Okay. So this student proposed a more smarter attack. So like I said, if you want to be the security expert, be first attacker, yeah, then you can develop the best defense. So I asked him to develop the attack methods first. So he named the approach called like dynamic frame alteration. So again it's a bit similar to the previous one, the last one, where you alter the frames after some point, but in that one it's kind of done very abruptly, it's not identifying any nice moment, yeah. But in here, when some kind of video is running, he has a stored video, he tries to find out the right time. So when like the contents of this one and content of the stored one are quite similar, or there are a lot of similarities or feature similarities, then you replace. Then it's not easy to detect, okay. So that's how it happens. So the camera is attached to Raspberry Pi, yeah, and there is some video storage and there is this module that is running, yeah, dynamic frame alteration. So what it does, basically it computes two things. Yeah, one is something called structural similarity index metric. Yeah, so it's basically how much is similarity of the incoming video with the stored one. So like frame by frame. Yeah, and it also checks the frame difference. So like what is now, what was the previous moment. Based on those two, basically he decide the moment when he can replace the incoming feed with this one, and then it's not easy to detect, yeah, because they are quite similar. Okay, as it's like something is getting executed, but after some time the stored video is blended and it's done seamlessly, like I said, using these two metrics, and then it stays undetected. Okay, so this one has like a real life demo, but I can't show it here. Yeah, but this is like one way to attack this video manipulation. Okay, and this is the result about detection accuracy. Yeah, so this is like detection accuracy of different approaches. So like so these are basically LOF, SVM, KNN, and this is average. Yeah, so these are the detection approaches. Yeah, I think this one is called least of frame something. This is support vector machine. This is K nearest never. And then you have these attack types. Yeah, replay, frame injection, video stream hijack, and DFA. So we apply that and apply this detection approach and check like what is the detection accuracy. So like out of 100 times, how many times this can detect. So you can see here, like for existing ones, the detection accuracy is very high, whereas in DFA accuracy is very low. That means lots of time this approach cannot really detect this dynamic frame alteration approach. Yeah, similarly support vector machine, almost similar results. Yeah, and again similarly with K nearest never. Okay, yeah, so this is one way to attack. Again, this is kind of trying to mimic the real feed. Yeah, coming very close to the real one but replacing it with something else. Now imagine what can happen if you do that. Yeah, if there is a flood monitoring at the server or at the base station, it will say there is no flood, so it can lead to more problem. Yeah, and if it's a bank, you know, like, yeah, you can rob the bank. Okay, so this one is again the same result in table format. I think we don't need to look again. Yeah, that was plotted previously. If you want to look more details, this is in this paper. Yeah, again this one and the previous one, continuous authentication. Now that was published somewhere else. So this is again like some cyber security conference, I think just happened last month or something. So this is published there. I think this paper is also available online. Okay, so again we are not going into lots of details. Yeah, there are a lot of libraries like Python and what kind of video feeds we stored and what exactly is monitored. All the details are in the paper. Okay, any questions? No? Okay, now next one I thought to cover attack on AI models. So nowadays you cannot live without AI models, right? But attackers are finding a way to attack these as well. Okay, so let's see how these things can be attacked, the AI models, and then how we can stop that. Yeah, how we can detect and prevent. So the one we are going to look is called something like prompt injection attacks on large language models. Okay, so large language models we all use, yeah, like OpenAI or Gemini. So any chatbot is using large language model. Yeah, but lots of them can be attacked with doing something like prompt injection. Okay, so what exactly it is? Do you have any idea what is prompt injection attack? If you don't know, I'm going to cover, but just wanted to check if you have heard about it. I will throw that slide in case you want to answer something. You can search on internet very quickly, again on large language model also, on ChatGPT you can search what is prompt injection attack. I think nowadays if you look at the models, they have become more robust over the time, but when they were released there were huge instances of prompt injection attack, and if there is any model new that is coming in the market, it's very prone to prompt injection attack. Any idea what do you think it is? Good, that's a perfect definition, yeah. That's perfect. So writing a prompt which can break any existing rule of the large language model. So for example, these large language models, they should not be giving answer for everything, right? If you say like, how do I murder this person, then it should not give the answer, yeah. Or you search like, how do I make a bomb, then it should not give the answer, yeah. So there is a rule, it should not give answer for everything. So now how you can write a prompt in a way it still gives you the answer, yeah. So they are not still very intelligent, so it's like you want to find out something, put some words before it, put some words after it, or ask the same query in a different way. Don't write bomb word, yeah, that is alarm to that. Write something else, yeah, maybe explosives or something else, or some other term that is not alarming, yeah, then it can give you the answer, yeah. So that is basically prompt injection attack. So you kind of curate your prompt in a way these large language models can give you the answer, okay. Good. That's another nice definition, tricking an LLM using a prompt, not directly, okay. Yeah, that's the same thing. So try to do some attacks onto these large language models. I think you cannot do the ones that are now very popular, ChatGPT or Copilot, because these have been trained from a long time. But some that are released like recently, not well trained, or these rules are not well defined, you can still use it, yeah, okay. So there are still some large language models, okay. Let's see, it goes next slide. Oops. So like we already have seen, yeah, these are techniques to manipulate large language models by inserting adversarial prompts. So you curate your prompt in a way, so you manipulate the large language models, yeah. What exactly will happen? They may leak confidential information, or they can ignore instructions, or they can execute malicious behavior, yeah. So something that the large language model is not supposed to do, if you kind of manipulate large language models in the form of like writing the prompt in a different way, it can give you the answer, yeah. So that is basically prompt injection attack. So if it's happening, we need to detect it, right. So let's look what are the limitations of previous detection systems, yeah, that are basically detecting prompt injection attack. So previous systems are relying heavily on linear or surface analysis of prompts. So it's like in your prompt there are a lot of words, right, they do some sort of linear analysis, yeah, like one after another each word, yeah, or like I said, there is a one word like bomb or murder, something like that, they rely based on that, yeah. And if they do that, they often miss kind of non-context dependent attacks. Okay, so they cannot work well. Okay. So what we typically want to achieve, yeah, so we want to achieve high accuracy detection of adversarial prompts in large language model workflows, yeah. So we want some detection approach that should be very, very accurate, yeah, and you have to be careful to develop that because sometimes if you are overprotective, right, anything you ask the prompt or large language model, it may say, sorry, I cannot give you the answer, sorry, I cannot give you the answer. That's one way, yeah, but you have to be giving the answer when you are supposed to do. Okay, so the accuracy is very important, yeah, so you should not have like false positive, yeah, don't say like it is an attack whereas it is not, because if you say that, you are not going to give the answer. Okay. So again a question, so how adversarial prompts can be detected in large language model workflows? Any ideas, thinking? So what exactly it is, yeah? You are typing something in the chat GPT, yeah? So but that is not a simple word, yeah? You are kind of twisting it in a way it should give the answer whereas it's not giving. Okay. So I mean there is like, even if the words are twisted, how can you make sure it doesn't give the answer, yeah? So how that can be detected, like even the twisted words have some kind of malicious intention. Okay, let me throw that slide. Okay, any idea? Okay, sentiment analysis of input prompts. That means you exactly work in this field. That's, yeah, nice. So actually the thing is, yeah, so you kind of take the all words, yeah, don't literally go with the linear analysis, yeah, you find out what is the sentiment of all of it, yeah, whether it want the answer that's going to come, whether it's going to do some harm, yeah, to someone after that person knows the answers, yeah. Using LSTMs, not sure how it can be detected, yeah. Natural language processing, I would say natural language processing is part, this is large language model, right. Training the LLM regularly, I think this one is nice. So you know, like sometimes they are giving some answers. If you train, basically it's just going to give you better answer, yeah, but maybe you can also train in a way it should not give the answer if it's the prompt is in just kind of modified way. Okay, what is this RLHF during training? I don't know what is this RLHF. Maybe some kind of rule defining during training, yeah. Okay, but I think you have some ideas, yeah. So sentiment analysis is kind of more powerful, yeah. You kind of have the sentiment of the word that is typed, and then based on that you can decide. Okay. So again, one of my master's student developed some approach. He also used this sentiment analysis. Okay. So let's see that approach we can briefly cover. Yeah. Don't know how much time we have. We have some time, yeah. Takes a long time to go. Oops. Okay. So the proposed approach is called novel GNN based detection framework. Yeah. So how exactly it works? So we take a data set. Yeah. So data set is of prompts. Yeah. They're like, and there are some kind of, you can say, malicious prompts and some non-malicious prompts. So everything is there. I think this data set has like 5,000 prompts that we have taken. So then we do some pre-processing of the data set. So first we do the duplicate removal. For example, if in your questions there are lots of same words or same basically meaning words, you can try to remove that. Yeah. And then you can do text normalization. So this is something is done already. So if there are some kind of uppercase letters, you make everything lowercase. Okay. And then you do some tokenization. So tokenization is something like out of all the words in the prompt, it's going to make tokens. Yeah, it's like first word is one token, or if there's a maybe long word, then it can make two tokens. Yeah, so the first subword is one token, second subword is another token. So you do that tokenization. Yeah, and after that is done, you do some graph construction. Yeah, so it's like each token is a node in the graph, and then here there are a few steps that are done. So these are not novel. Yeah, this is like BERT embedding extraction and edge construction. These are already well popular. Yeah, there are libraries to do that. So from that tokens, like you can say all the nodes, from this graph construction, we capture semantic and contextual relationship between the tokens. Yeah, I think someone said like sentiment analysis. Yeah, so this is very close to that. Yeah, so these kind of relationships are captured. Yeah, so this BERT embedding that is already available provides a rich contextual representation that captures the meaning of words based on their surrounding context. Yeah, and here sentiment features are also incorporated into the node representation. Okay, and finally edges between the nodes or tokens are established, ensuring that local contextual dependencies are preserved. So again, we are not going in detail, but for each step there is a process. Yeah, but in summary, it's like whole prompt is made into tokens, and a graph is made out of it, and within each node we capture contextual relationships. Yeah, and then that graph is fed to a GNN model. Again, in our GNN model, it's well defined in the paper. So that GNN model is trained. Yeah, like I said, we have around 5,000 prompts. Out of 5,000, we have taken like 80-20, 80 for training. So for all 80% of those 5,000 prompts, we do the same step, and then one GNN model is trained for that. Yeah, and then that GNN model is basically going to tell, based on these features that are captured, whether it is basically kind of malicious prompt or it is not a malicious prompt. Okay, I think maybe we can stop here. There are just one or few more slides I will cover tomorrow. Okay, yeah, all right, okay, so we stop here.